I have fluid that's not only in my plasma, but in my bloodstream that is far less concentrated than my cells. Burst, rupture, swell, edema, right? So if I put a lot of dilute fluid in my blood plasma, maybe with, say, 0.5% sodium concentration, that is less than what my cell has. In other words, it is hypotonic to my cell. So the water will move from my blood plasma into the surrounding interstitial tissue space, and then from there it will be pushed into my cells where the cells will bloat. So the problem with hypotonic hydration is you not only flood your cells and tissues with all this excess fluid, the kidneys can't process all this fluid quickly enough to get rid of it, and here's the danger. All this excess fluid gives you hyponatremia. All right, heard of that word before? Hyponatremia. Hypo is what?
Too much. Too
low. Gives you low sodium. So in essence, drinking tons of fluid over a very short period of time washes away your salt. If you wash away your salt, then you leave the fluid even more dilute. So it really makes the problem worse if you're drinking lots of fluid over a short period of time.
So that's what makes it hypo, because you lose the sodium.
You lose the sodium. Wash it out. You wash it out, yeah. You know, hazing, contests, all sorts of things have people finally realized that hazing with alcohol can actually kill people, duh. So they switched to other things like making people drink milk or water, which they think is harmless because, you know, who's ever died of drinking water, right?
It's happened.
Yeah, it's happened. A couple of years ago they had the Nintendo Wii contest out in California, and the joke name for it was Hold Your Wii for a Wii. And they gave people gallons of water and said drink and don't pee. And whoever doesn't pee gets the Nintendo console. And at that point, they were hard to find, and you know nobody could get one, so people were joining this contest for the radio station. One 28-year-old woman with 3 kids went home and died because she had drunk a couple of gallons of water during an afternoon's period of time, had a horrible headache, and of course it was all this condition of water intoxication and hyponatremia. What did the headache come from?
Fluid that moves outside of the cells.
Yeah, too much fluid in the brain, it collects outside the cells and moves in, and once those cells start to swell, then you get edema on the brain. Too much fluid can actually push your brain down into the foramen magnum. Down there is your brain stem. Bye-bye brain stem. It shuts off vital function for the brain stem, and it crushes cerebral cortex activity on the outside surface.
What could she have done?
If they had caught this quick enough, hook her to a hypertonic salt solution and sucked her dry, if they had caught it quick enough.
Children have a tendency when they're playing in swimming pools
to
get that because they're gulping water and inhaling water, and then they go home and lie down and the parents think they're tired, and it's because they have hyponatremia.
That happened or did somebody swallow in pool somewhere?
In Myrtle Beach, I think.
Oh, really?
They were visiting Myrtle Beach,
wow.
But it's happened a lot.
Water drunk. Scary, yeah. And mentioning that, you know, people will go out in the yard on a hot summer day, work like crazy, not stop and drink periodically, come in the house and say, man, I'm thirsty, and they drink the first thing they can find.
Get a bad headache, don't they?
Get a bad headache doing that too, yeah, and that's water intoxication too. So it really messes with your fluid and your sodium balance. So yeah, drinking water is great if you do it at a steady rhythm and spread the water out over the, you know, at the day's time. But drinking a liter of fluid at one sitting overwhelms your system and you can't really process it.
If you like your construction workers and people that work outside, they'll use the salt packs and then continue to drink.
That's smart. Then at least that way you're not giving yourself hyponatremia. Got a new term here for you. We've talked about edema off and on during the semester, but here's an official definition for you. Let's say that you've had a liter of fluid over the past 5 minutes. That fluid accumulates first in your bloodstream because it was absorbed by your digestive system. That fluid will then move to the surrounding cells and tissues outside of the bloodstream because as we travel through the capillary, we push fluids out at the arterial end that now accumulate out here in the interstitial space. That fluid can then move into your cells. Hey, if it's hypotonic solutions make cells swell, and then we're looking at an issue of having edema or swelling in the tissues and the surrounding spaces.
What about the lymphatic system?
It may be overwhelmed trying to pick up excess fluid, so you're just talking too much fluid in general out in the tissue space.
Okay.
So yeah, it may be trying to do what it can, but it's probably just a flood of too much fluid. Okay, so a little bit about edema there. Part of the problem with edema, you'll notice the very last bullet point down there, things like proteins that leak out into the extracellular space can actually pull water out into that space with it. Anytime you've got blockages in fluid flow, like if you've got a blockage in one of your lymphatic vessels, you can't get extra fluid back in lymphatic flow. So there's other conditions just besides drinking excess water over a short time period that can lead you to a case of edema that's oftentimes very hard to reverse and get rid of. Water is one issue. That's what we're talking about here on 128. Not enough water is dehydration. Too much water can lead to edema, or too much water in the interstitial space can lead you to edema. Let's go over a little bit about electrolytes there on the top of 129.
I have a question about the one we were talking about proteins and things like that.
The ECL? Okay. How could you get proteins out? What kind of pressure must you have in the blood vessel to get proteins pushed out? Yeah, it'd be hydrostatic pressure. Would it be high hydrostatic or low?
It'd be high.
There you go. That's how proteins escape. So you may have high blood pressure pushing so hard that it's not just fluid escaping the capillary. It may also be proteins or even sites that maybe shouldn't be traveling out there.
Well, the water will pick up all of it.
Yeah, everything. Then of course, if you get proteins, then you're right, everything follows it. Does that make sense? And there's other conditions like lymphedema that result, once the proteins are out here, they can't get back in. So it's kind of like, they're stuck, and they're constantly pulling water to keep with them out there as well.
So there would be high hydrostatic pressure to be able to come in.
Yes. Or even high hydrostatic pressure at the arterial end, and it's so high that it counteracts the osmotic pulling it back in. So yeah, it would ultimately be the venular end tube. Quick trip to chemistry, back in Bio 210 for just a moment. Covalent bonds versus ionic bonds. What type of bond breaks down and forms ions? Bingo, right? Ionic bonds form ions. Covalent bonds are most of our macromolecules, carbohydrates, proteins, lipids. Most of those actually are covalently bonded. For that reason, we do not include them in the list of electrolytes here on the top of page 129. Covalent bonding means that the parts of the molecule do not ionize or break apart because they're sharing electrons rather than transferring electrons. Now, in the category of electrolytes, you might recall from 210 we talked about acids, bases, salts. They all are called ions because they can break apart or dissociate into their building blocks, maybe atoms of sodium or chlorine, for instance, when they're dissolved in water. So compounds that are covalently bonded are called non-electrolytes, while ionic compounds form electrolytes. Which one of these do we need for water hydration? Yep, electrolytes, good. Let me show you why we need electrolytes. Glucose, non-electrolyte. It does not break apart in water. So if I put this in a watery solution, I still have C6H12O6. It's covalently bonded, so it's not going to break apart on it. If I put salt in solution, you know what salt does, right? salt breaks up in solution and it gives me an ion of chlorine and an ion of sodium. So think about your pulling power. We know from discussing osmosis in 210 that solutes pull water to wherever they're located. This is considered one single unit, okay, because it does not break apart. It's just a glucose molecule. But if you put salt in water, I have two separate units. Who has more pulling power?
Salt.
Salt, yeah. So if you put an ionic compound, whether it's an acid, a base, a salt in your body, those have more pulling power to keep water in their compartment than do non-electrolytes like glucose, carbs, proteins, lipids, and all those that we consider to be organic compounds. So the interesting thing here is that we're talking specifically about inorganic compounds that break apart or ionize in water. They have more power to pull water to their compartments and keep that water there. And that's actually detailed down at the bottom of your page under numbers 2 and 3. And before we leave that page behind, you will want to highlight and know the cations and anions up there under number 2. I give you a clue to remembering these. Cations are positively charged, anions are negatively charged. If you think about it, this is all common sense. When you're talking muscle and nerve impulse, all that stuff we talked about, sodium rushing into the cell. Hey, if sodium's rushing in, where was it at? On the outside, you can see that it's one of the major ions in the interstitial fluid. Where's calcium stored? Bones. Okay, so it's an extracellular type of ion as well. The way I keep potassium and magnesium straight, I keep P and M in my brain because PM reminds me of plasma membrane. These two ions are inside your cell, so they're inside the plasma membrane. You got to have some kind of trick, right?
You said P and M?
Yeah, see where it says potassium and magnesium are in the intracellular fluid? I just remember that P and M means plasma membrane. These two are inside your plasma membrane of your cell. And keeping with the P trend, phosphate is also intracellular. That's another one of those negatively charged anions. For Tuesday, what you might want to do is just look at page 130 and just read through, see if you've got any questions about the bolded terms on that chart. What I'm going to do with you Tuesday is we're going to get into the nitty-gritty. We're going to work through 131 through 133. So bring your thinking cap on Tuesday. We're going to hit the heavy-duty stuff.
All right.
All right, y'all have a good weekend.
You too.